All right, hello everyone. So I'm going to go through this practice exam and give a video solution for it. So before I start, let me do the usual warning, which is that the practice exam, okay, is not going to be a carbon copy of the actual exam. It is going to have generally similar / the same content. But it's not going to ask questions in the exact same way. You shouldn't expect the exam to look exactly like the practice exam. It's just a selection of problems which roughly covers most of the items which we've learned in chapters 3 and 4. If you want to see a list of things which you should be studying for the exam, then go to the Blackboard page, and I posted a bulleted list with some items which are basically non-negotiable for the exam and some items which you should also be aware of. So you can find that on Blackboard if you need. Okay, so let's just get started. So question 1, we have a cubic polynomial here, so power 3, and we are supposed to find all the critical points of this function and classify each critical point as a local min, local max, or neither. And just like this problem, I'm not going to specify on the exam whether you have to use the first or second derivative test, so maybe I'll just do it both ways. So the first thing we need to do is find the critical points. So the first thing I'm going to say is that f of x is a polynomial. So f prime of x always exists. Okay, I can tell it's a polynomial because the powers here are integers and non-negative. So I don't need to worry about the situation where I have a critical point that's caused by the fact that the derivative does not exist at that point. So I just need to check for the places where is the derivative equal to 0. So that I'm going to find the derivative. So f prime of x, I'm just going to do the power rule. So x cubed becomes 3x squared, and minus 3x becomes just minus 3. Okay, and now what I want to do is set this equal to 0, and this tells me that, well, I can factor this, or I can take a 3x out. No, I can't. I can take a 3 out, sorry. And I'm left with x squared minus 1, and that's a difference of squares. So I get 3 times x plus 1 times x minus 1 is equal to 0. So if I take 3 numbers, I take 3 times a number times another number, and I get 0, then one of the two numbers that I multiplied at the end had to have been 0, so I just set each of those equal to 0. I get x plus 1 equals 0, that tells me x equals 1, and I get x minus 1 equals 0, and that tells me x equals minus 1. So one of those two things is true in order to make this equation equal to 0. Okay, so those are my critical points. So these are my critical points. And now I need to classify them as a local min, local max, or neither. So I'm going to first do the first derivative test. To do that, what I'm going to do is I'm going to make a number line. I'm going to put my critical points on here. It's -1 and 1. And I'm going to choose test points from each sub-region. Okay, so one has to be to the left of -1, so say maybe -2. One has to be in between, maybe 0, and one has to be to the right, how about 2? And I'm going to check what is the value of f prime at each of these locations. Well, f prime of -2, if I plug in -2, I'm going to get 3 times 4 is 12 minus 3. Okay, I'm just plugging in -2 here, so I square it, I get 4, multiply by 3, I get 12, subtract 3 from that, I have 9. So this is 9, which is a number which is bigger than 0. And then I have f prime of 0. If I plug in 0, I get -3, which is a number which is smaller than 0. And then finally, for at 2, I get the same thing as before, right? I think I get 9. Okay, so the first derivative is positive, then negative, then positive, which tells me that the function is increasing and then decreasing and then increasing. So by this logic, I can conclude that x equals -1 is a local max, and x equals 1 is a local min. Okay? Because if we're going down and then going up, it's a minimum. If we're going up and then we're going down, we must have reached a maximum. So that's the first derivative test. How would I do it using the second derivative test? Well, using the second derivative test, I would take the second derivative, which in this case is going to be, I just take the 2, comes down, it becomes 6x. So what I do for the second derivative test is I'm not going to take test points, okay? I'm going to actually plug in the critical points. So I'm going to do f double prime of 1, and I get 6. And I'm going to do f double prime of -1, and I get -6. Now what this tells me, okay, is that, respectively, f is concave up at x equals 1, and f is concave down at x equals -1. Now, if we're concave up, okay, then we look like this. If we're concave down, then we look like this. And that's how I can tell that this is going to give us a min at x equals 1, and it's going to give us a max at x equals -1. So that's the second derivative test. So the main difference between the first derivative test and the second derivative test is for the first derivative test, we make our number line, and what we're going to do is we're going to put the critical points on the number line, but the numbers that we plug in need to be numbers which are in between the critical points, okay? So we have to pick these test points. But for the second derivative test, we're actually going to take those critical points and just go ahead and feed them straight into the second derivative. Okay, so this is how we find and classify the critical points. So we didn't have any neither. We just had a local max and a local min. Okay, so now we need to find any inflection points of the function if they exist. Now, to remind you, we have an inflection point, okay, when f double prime changes sign. Now, if I have a function and it goes from being positive to being negative, then in between it must have momentarily passed through 0. So the places where I'm going to check to see, oh, where did we go from being negative to being positive, or from being positive to being negative, are going to be the places where maybe I touched 0. Now, if I touch 0, it doesn't necessarily mean that my function went through the x-axis and became negative, or went from being negative to being positive, but it's a necessary condition. So I look for the places first. I solve f double prime of x equals to 0. And I find the places where I might find an inflection point, and then I'll verify later. So f double prime of x, remember, was 6x, so we set that equal to 0, and that tells me x should be equal to 0. So now I need to check, is x equals to 0 an inflection point? And what I need to do is, again, use this number line method. So what I want to check is, well, is the concavity on the left different than the concavity on the right? And to do that, I need to check what is the sign of the second derivative to the left and to the right. So I'm going to pick two test points, -1 and 1, and plug them in, and I can tell from the last example, okay, that f double prime of 1 is going to be 6, and f double prime of -1 is -6. So the second derivative goes from being negative to being positive. So f double prime changes sign at x equals 0. Therefore, x equals 0 is an inflection point. Done. Okay, so that's that problem, really standard stuff. Yeah, probably going to be some kind of question on the exam asking you to find critical points and classify them, find inflection points, and use one of these tests in some kind of way. Okay, question 2 is some true and false. I always put a true and false for the second question. So let's just go ahead and do it. All right, so the first one says a critical point x equals p of a function f of x always corresponds to a maximum or a minimum of the function f of x. This one is false. Okay, a maximum or a minimum is always going to occur at a critical point. But just because we have a critical point does not mean that we get a maximum or a minimum. Okay, and here's an example. F of x equals x cubed is a function that has a critical point at x equals 0, but it doesn't have a maximum at x equals 0. So it looks like this. Okay, but if you take the derivative, you get f prime of x equals 3x squared. If you set it equal to 0, this tells you that x is equals to 0 is a critical point. But is clearly not a maximum or a minimum of the function. So that one's false. Next up, we have if f prime of a is larger than 0, then f of x is concave up at x equals to a. Not necessarily true. I can have f prime of a larger than 0 implies that f of x is increasing at x equals to a, okay? F double prime, if f double prime was positive, then f of x would be concave up. So this one's false. Next up, we have a very common mistake in calculus is, okay, we say, we tell all of our students, yes, the easiest derivative that you can possibly do is the derivative of e to the x. It's just itself. Okay, but that only works for e to the x. When we have e to the kx, okay, then we need to either use the e to the kx rule or the chain rule. So whichever way you think about it, the derivative of e to the kx is going to be k times e to the kx. Okay. So this one's false as well. I forgot an E on this, false. Okay, so D, the derivative of a polynomial is a polynomial. Okay, so this is a great question. And it is true. To see that it is true, let's just think about what the definition of a polynomial is. We said it would be an times x to the n plus dot 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 plus like a1x plus a0, right? So the question is, if we take the derivative of this thing, are we going to get something else which is also a polynomial, meaning that it also has non-negative integer powers? Well, if the power is n is a non-negative integer, then n minus 1 is also a non-negative integer all the way up to the a equals, or to the n equals 0 term, right? But if we think about that constant term, okay, when we take its derivative, it's going to go away. So we're never going to wind up with negative powers of x. And since all of the positive powers of x are integers, if I take n as an integer and I take 1 less than it, well, 1 less than it is also going to be an integer or a natural number. Okay, so this one is true. All right, the equation of the tangent line t of x to f of x at x equals a is given by t of x equals f prime of a plus f of a times x minus a. This one is false. We need to have this equation memorized for the exam, only this one's not quite right. The f prime of a and the f of a are switched. So it should be t of x equals f of a plus f prime of a times x minus a. And the reason you can remember that is because what should get multiplied by x, right, if you multiplied this out, what should get multiplied by x would be the slope of the line. And the slope of the line is, of course, the derivative. So that's how you remember the derivative should go here. All right, so that's true and false. Question 3. Radio House finds that their cost function can be modeled by the function c of q equals 1.25q plus 10. So, if we remember from our class, we had this rule. Of course, we have an exponential function here, but the problem is this exponential function, the base is not e. So we can't use the e to the x rule or the e to the kx rule. So there's two ways around that. You can either remember the a to the x rule, right, which said that the derivative of a to the x is going to be equal to a to the x times ln of a. You can either remember that, or you can use the following method. You can also say that a to the x is e to the ln of a times x, and that derivative would be e to the ln. So if I do the derivative, that derivative would be e to the ln of a times x times ln of a, and then this is equal to a to the x times ln of a. So that's the other way that you can think of this, okay? You just replace a by something which is equal to e to the ln a. I just get a. Okay, so that's how you can remember how to do that derivative, which is what we're going to need to do here, because marginal cost, okay, marginal cost, that's just the derivative, okay? And if they say at a production level of 20 radios, they're asking us to do c prime of 20. Okay, that's our goal. So first we need to get c prime of q, which is the 10 is going to go away, and we're going to use our a to the x rule. We get 1.25 to the x times ln of 1.25. So if we want to get c prime of 20, we just got to plug in 20. 1.25 to the 20th power times ln of 1.25. And if you want to just leave it like this on your exam, that's perfectly fine. Or if you want to calculate it out using your calculator, that's also okay. But what I need to see happen on a problem like this is we need to find the marginal cost function and then plug in 20. Okay, so if you do all of that and you get to here, I'm not really worried about whether or not you know how to take something to the 20th power and multiply it by something else. Like, that's middle school level math. Okay, so maybe it's not middle school level math. That's a simplification. But anyways, I'm confident that you all know how to do that, and you don't need to demonstrate that to me on an exam. So, Radio House finds that the revenue function can be modeled by the following function. R of q equals q squared e to the q. Okay, and we're supposed to find the marginal cost. This should say marginal revenue. Sorry. For a production level of q radios. Okay, so in this one, we're not supposed to plug in 20. We're just supposed to find it in general. So, of course, the marginal revenue is nothing but r prime of q. So if r of q is given by q squared e to the q, I need to take the derivative of this function in order to get r prime of q. So the way I'm going to get the derivative of this function is I'm going to have to use the product rule, because I have q squared times e to the q. I know how to do the derivative of q squared, and I know how to do the derivative of e to the q, but we're multiplying them together. So we need to use the product rule. So the product rule, remember, says that the derivative of two functions being multiplied together is do the derivative of the first one, leave the second one alone, and then plus leave the first one alone and do the derivative of the second one. And the neat thing about the product rule is if you accidentally mess up the order, you're not going to be in trouble. But you need to remember that if you do mess up the order in the quotient rule, you will be in trouble. So product rule is more forgiving in that sense. So the first function is, okay, if I was going to do this, I would say f is going to be my q squared, and I'd say g is going to be e to the q, right? So f prime is 2q, and g prime is e to the q again. So I just need to take these things and multiply together. So first up is 2q times e to the q, that's f prime g, and now I add and I get fg prime, which is q squared e to the q. And I'm done. So that's just a simple product rule. So next up, they say, based on our answers to part A and B, we're supposed to write an equation for Radio House's marginal profit function. Okay, now this one takes a little bit of a higher theoretical jump than the other ones. These ones are mostly computational. But to remember this one, okay, what we need to remember is what is the relationship between the profit function and the cost function and the revenue function? Well, the profit function, pi of q, we know is just equal to r of q minus c of q, right? That is our profit function. We take our revenue and we subtract our costs. So if I want to know what is the derivative of the profit function, what I need to do is do the derivative of r of q minus c of q. And since I know that I have the sum rule, which says that the derivative of two things, or sum and difference rule, which says that the derivative of two things being added or subtracted from one another is just going to be their derivatives being added or subtracted from one another, I get just r prime of q minus c prime of q. And these are functions which I calculated in the previous two steps. So I get let's see, 2q e to the q plus q squared e to the q minus 1.25 to the q times ln of 1.25. All right, so that's my marginal profit function. So remember, marginal profit, marginal revenue, marginal cost is just the derivative of the profit, revenue, and cost functions, respectively. Okay, question 4. Maybe one of the harder questions that's on this big practice exam. So we have the volume of a sphere is given by v of t equals 4/3 pi r cubed, but r is also a function of t. Okay, so we're supposed to assume that the radius of the sphere increases in time according to the function r of t equals t to the 7 plus e to the 3t. Okay. So we need to find the derivative of this volume function. So there's a couple ways that you could go about this. The first way would be to leave r alone for the time being and notice that d dt of 4/3 pi r cubed, r of t cubed, is the same as, well, the constant can come out, okay? So 4/3 times pi is a constant, so I get 4/3 pi. And now I need to do the derivative of r of t cubed, which is, of course, going to be an application of the chain rule, because I'm taking a function and I'm cubing it. So to do its derivative, I would get 4/3 pi times 3r of t squared times r prime of t using the chain rule. Okay, and now I could identify, well, r of t is our t to the 7th plus e to the 3t, and therefore r prime of t is 7t to the 6th plus 3e to the 3t. So this is then equal to 4/3 pi 3 times t to the 7 plus e to the 3t to the second power times, all with parentheses of course, 7t to the 6 plus 3e to the 3t. So that's one way of doing it. It's just kind of doing it generally using r of t. And the other way to do it would be to start by just plugging in what r is. So you'd get 4/3 pi times t to the 7 plus e to the 3t all cubed. And now we need to do this derivative, so d dt of this guy. So if you want to do it this way, there's two ways you can do it. The first way would be to literally FOIL this out 3 times, which would be really painful, I think, and you're highly likely to make a mistake. The second way is to basically do this, but well, apply the chain rule, except not using the function notation r of t, but actually using the function t to the 7th plus e to the 3t cubed. So once again, the way I would do that is 4/3 pi is just going to hang out. And then what I would do is I would recognize that t to the 7th plus e to the 3t is the inner function. So what I need to do first is the derivative of the outer function first, where I leave the inside alone. So that becomes times 3. We leave the inside alone, t to the 7th plus e to the 3t, and I make the power 1 less. And now what I have to do is multiply by the derivative of the inside, which of course is 7t to the 6th plus 3e to the 3t. Okay, so we got the same thing. Just a standard kind of chain rule problem. But for some reason, I've noticed that a lot of students sometimes gets tripped up when things get geometric. But really, I didn't do anything with geometry here at all, right? All I did was take the equation and manipulate it. Okay, so next up, we're supposed to write a formula for the derivative of a triple chain rule or a double chain rule. Okay, so this is the exhibit problem where we got a chain rule and no chain rule. So the way we want to do this, okay, is just like how we would do any other chain rule. So we start by recognizing that the outer function is going to be p and our inner function is going to be q of r of x. If we treat it that way, then the derivative of this should be, of course, the derivative of the outer function where we leave the inside alone. And we need to multiply by the derivative of the inner function. And the reason I write it like this is because in order to do this derivative, I'm going to need to apply the chain rule again. So if I do that, it's as simple as rewriting this first part. Do I have enough parentheses here? No, I need one more. In fact, I need one more here too, right? Yeah. Okay, so to finish this off, what I need to do is multiply, and I need to write down what is the derivative of q of r of x. Well, that's just a regular chain rule, so it becomes q prime of r of x times r prime of x. And I'm done. Okay, so this is something that you can memorize too. So if you were really worried about a double chain rule showing up on the exam, then simply memorize this formula and make sure that you know how to identify the inner, the middle, and the middle, and the outer function. Okay, so for the next part, question 5, we're supposed to find the equation of the tangent line. Okay, so that's almost definitely going to show up on the exam, okay? Equation of the tangent line to a function at x equals something. In this case, the a value is just the number e, okay? And the function is f of x equals ln of x over x. So the first thing I need to do is, well, the first thing I like to do is to write down what the equation of the tangent line is. So it's f of a plus f prime of a times x minus a. And in my particular circumstance, I have a, the number a is e. Okay, so for me, I'm going to rewrite this. T of x equals f of e plus f prime of e times x minus e. So what I need to do in order to finish this problem is to find out what are the numbers f of e and f prime of e. If I've done that, then I'll be finished. So f of e is easy enough. All I have to do is plug in e to the function. So I get ln of e divided by e. Now this is a situation where we need to remember our log rules, right? So ln of e to the x, okay, we had a rule which said that ln of e to the x is just x, right? These are inverse functions. So if I do ln of e, that's the same as ln of e to the 1, which is just going to be 1. So ln of e is just 1, so I get 1 over e as f of e. Now, in order to get the other part, which is f prime of e, I need to, of course, take the derivative of this function. So let's do that. I'm going to do it using the chain rule, not the chain rule, excuse me, the quotient rule, which says I get low d high minus high d low all over low squared. So in this case, my low function is the denominator, which is x. So I get x times derivative of ln x is 1 over x. Then I get a minus sign. And now I write ln of x, that's high. And I multiply that times the derivative of x, which is 1. And now I divide all of this by x squared. So if I simplify this a little bit, that's just 1 minus ln of x all over x squared. So if I want to find out what f prime of e is, I just need to plug e into this function. So I get 1 minus ln of e divided by x squared. So if I remember from the previous part that ln of e is just 1, this is just 1 minus, I'm sorry, not x squared, it should be e squared in the bottom. So I get 1 minus 1 all divided by e squared, which is 0 over e squared, which is 0. So the derivative is 0. So in the end, t of x is just going to be the function, the line, 1 over e, because this guy is 0. So this is a number. So if I have a line which is equal to a number, that just means that this is a horizontal line with height 1 over e. Okay, so that's a quick tangent line problem. Memorizing this formula here is going to be crucial for the exam because there's going to be a tangent line problem on the exam. Okay. On the graph below, we're supposed to draw a function satisfying f of x has a critical point at x equals 2, f of x has an inflection point at x equals 6, and they tell us some other information. They say that to the left of x equals 2, the derivative is negative, and to the right, it's positive. Okay, so let's pick a point, a height for our point x equals 2. I don't know, maybe I'll put it here. That could be, they don't specify, wait, is this just gonna, okay, there we go. They don't specify what the height of the function should be. They just tell us that there's a critical point there. So it could be a minimum or a maximum, and the way we need to figure out whether it's a maximum or a minimum is by looking at what the derivative's doing to the left and to the right. So they say the derivative is negative to the left and it's positive to the right. So f prime negative means the f is decreasing, and f prime positive means f is increasing. So f is decreasing to the left and it's increasing to the right. So this is a minimum. Okay, this means x equals 2 is a local min. Okay, so we have maybe a function which looks kind of like this initially. And how about the second part? They say we also have an inflection point at x equals 6. And they tell us that the value of f double prime is positive to the left. So that means we're concave up to the left, and f double prime is negative, which means we're concave down to the right. So maybe it would be better to draw this a little bit further down so that we have a bit more space to go up here. All that matters about this point is that it should be a minimum. So maybe it looks something like this. And then at x equals 6, that's 3, 4, 5, 6. The concavity should change. So maybe it's concave up, and then it starts to be concave down at this point. And that's not a great drawing. It's concave up, concave up, concave up, and then it's concave down. So this could be a function which satisfies these properties. Let's just double check. F prime is negative to the left of x equals 2. F prime is negative to the left. Yes, it's going down. F prime is positive to the right of x equals 2. Okay, f prime is positive to the right of x equals 2. So in fact, I shouldn't have drawn this part here, because this is to the right of x equals 2, but in this region the function's decreasing. So what I should have done was it should have gone up like this, and then maybe just off like that. Okay, and this way we maintain the fact that the function's increasing to the right of x equals 2, right? Because we didn't get any other information to say that it starts decreasing some point later on. Okay, and let's check the other ones. F double prime is positive to the left of x equals 6. So in this whole region, it should be concave up. So we did that, so good job. And to the right of x equals 6, it should be concave down. Okay, so it is concave down. All right, so this is how you do this process. And sometimes, like I had to do, you have to revise your drawing as you go along. You might have to erase and restart once you get a better idea of what it should look like, but you have to kind of piece it together from this information. All right, so last question. We just have some random derivatives. So the first question is a really pretty simple chain rule problem. All I have to do is recognize that the inside function is x plus 1 and the outside function is the power 2022. So this derivative is going to be given by, I take the derivative of the outer function first, which means I take the power down, I leave the inside alone, and then I make the power 1 less. And now I need to multiply by whatever the derivative of the inside function is. But of course, the derivative of x plus 1 is just 1. So if you don't want to write the last part, it'd be perfectly fine to just say that the answer is 2022 times x plus 1 to the 2021. So that's a chain rule. So ln of e to the 3x. Okay, this one you could do two ways. You could think of it as a chain rule if you want, by saying, well, I have an inner function e to the 3x and an outer function ln. So if you want to use the chain rule, you can do that, and you can say that this is going to be 1 over e to the 3x times, and now needs to come the derivative of e to the 3x, the inner function. So that would be e to the 3x times 3. So you would cancel these guys, and you would get 3. The other way to do it, which is smarter, is to recognize that ln and e are inverses. So if I do ln of e to the 3x, this is the same as just 3x. So if I want to do the derivative of 3x, then, well, it's just going to be the slope, which is 3. So two ways of doing this one. So don't forget that anytime you have a function like this, you can always try to manipulate the function before you take the derivative, as long as you don't change what it really means, which doing this is just rewriting the same function in a different way. All right, next up we have x plus 1 over x plus 1 to the 2022. So two ways you could do this. You could try to do it using the quotient rule if you want, or you can recognize that, of course, if I have something like x to the 1 over x cubed, right, then since I have the same factor in the numerator and the denominator, this would just become 1 over x squared, right? We would subtract 1 from 3 and get 1 over x squared. So I'm going to use the same principle. I'm going to use the same principle here because I have x plus 1 in the numerator and x plus 1 in the denominator. So I'm just going to rewrite this as 1 over x plus 1 to the 2021. And to take this derivative, I don't need to use the quotient rule. I can rewrite it as x plus 1 to the negative 2021. And to do that derivative, I just need to use the power rule again, and the chain rule, I guess. So it would become negative 2021 times x plus 1, and I make the power 1 less. It becomes 2022, and, negative 2022. And now we need to multiply by 1, which is the derivative of x plus 1. So that's a chain rule problem. Or you can do a quotient rule if you really want. You'll get the same answer. Okay, so next up we've got a chain rule and a power rule, basically. So I have e to the 1 over x. So that's like e to the x to the negative 1, and I have cube root of x, which can be rewritten, of course, as a 1/3 power. So the way I take this derivative is I do each piece individually. For the first one, I need to use the chain rule because I have a function inside a function. The inner function is x to the negative 1. So the derivative of the outer function comes first, so that's just e to the x to the negative 1, where I leave the inside alone. So this is just the derivative of e to the z, is e to the z, and I plug in the original inner function. And then I'm going to multiply by the derivative of x to the negative 1, which would be negative 1 times x to the negative 2. And now I'm going to add. And what I need to write now is the derivative of x to the 1/3. So I do the same thing that I always do with the power rule. 1/3 comes down, and then I write x, and then the power should be 1 less than 1/3. So 1/3 minus 1. 1/3 minus 1 is the same as 1/3 minus 3/3, which I just subtract the numerators and I get negative 2/3. So the power is negative 2/3. 1 less than 1/3. Okay, and the very last problem, we have square root x times 6x cubed minus x to the 7th power. This is a combination problem. We're going to need to use the product rule and the chain rule. Okay, so the way I'm going to split this up is by thinking, or the way I like to think about these is I think, okay, what do I wish this problem looked like instead? How do I wish this problem was different? And I think to myself immediately that this would be a lot easier if this square root x wasn't here. Then this one would just be a really simple chain rule problem. So I would know how to do that derivative if it was just on its own. And of course I know how to do the derivative of the square root function on its own. So I know how to do the derivative of each of these two functions if I separate them by a multiplication sign. So I'm going to do that, and I'm going to use the chain rule, not the chain rule, the product rule. So the product rule says first thing that you should write down is the derivative of the first function, which is just 1 over 2 square root x. Okay, that was a power rule. And then we leave the second function alone for the time being. Now I write a plus. Now square root x gets left alone, and what needs to come here should be the derivative of 6x cubed minus x, all being raised to the 7th power, which of course will be done using the chain rule. So I paste, and I'm going to replace this derivative by, well, its derivative, which is 6x cubed minus x, all being raised to the 6th power, times 7. And then I multiply that by the derivative of the inside, which is 18x squared minus 1. Okay, and I'm done. So, just a combination problem. We had to use the product rule and the chain rule on this one. All right, so that's it. I hope you found this useful. Good luck with your studying. If you have any questions on the practice exam, please bring them to the review or to office hours or to the SI sessions with Daria, or go check out the Math Tutoring Center. Just Google U of SC Math Tutoring Center, and there are free tutors available from 10 a.m. to 3 p.m. Monday through Friday. So as always, just let me know if you have any questions, and you can shoot me an email as well if you want some notes written out for you, and then I can do that. So yeah.